how many weeks we have and when the classes are ending, and I still have to do superconductivity. And I also have to balance that with spin transport, which we haven't yet done. But I looked at that material, which is here. This is our article. So there's a very nice article in the latest Physics Today, which I'm assuming everyone has because you're all a member. I guess Michael may not be a member. So you can get it. We are going to post it on the web.
Okay, yeah, I was going to say, like I said, I haven't gotten it from my parents.
Okay, yeah, so that's okay. Everyone else has it? You may not have it, you're not a... Okay. This is not this is not a pitch to become a member, okay? All of those who are in physics should be a member. But anyway, there's an article here on spin polarized tunneling, which basically covers all the ingredients in 3 pages. And what I thought we would do is break up that 3-page into, there are classic papers that they refer to here. So each of you will go through one of these classic papers. And then I was thinking, okay, we can have a presentation. We do want to have the presentation because otherwise the rest of us won't learn about it. So what I'm planning is basically we have the discussion on the homework tomorrow. Tomorrow is Thursday. We discuss this epsilon of omega, etc. homework tomorrow. And from Monday, I'm going to start superconductivity. Because that's a subject you cannot just read on your own, unlike the spin physics. Right now, with the nano discussions that we have had, you have enough background to just read that stuff and figure it out. It's very simple. We have all the information based on tunneling, based on, it's just a matter of saying, okay, I'm going to have the 2 leads not be fully unpolarized, meaning every state was equally populated with up and down. What if I make one population bigger than the other? It's not such a difficult problem that you guys can't figure it out with the background you have. But superconductivity is completely non-trivial. So that's the part I want to now start spending on some time from this coming Monday. And I'm not going to do the microscopic theory. That requires second quantization and it comes with its own set of challenges. But there are many aspects of superconductivity we can do just in terms of what is called an order parameter theory. So that's what I'm going to do. And then by the end of it, I will bring it down to tunneling through a superconducting dot. Just grab a chair. So that's the plan, okay? Now, let Andy come and then I'll tell you about this project idea. So, this is the... Are you recording this? I'm going to make some statements. Just, okay, you can record it.
They can be edited out
I
later.
don't want anyone, sort of then saying, hey, you said this and, going to sue you for this or none of those crazy things. But, okay, here's what I was going to say, is that I'm basically going to, I have assigned all of you a project today. Some of you I need to talk with right after the class, but practically everyone has been assigned a project. And this is because I was just saying, I don't have time to cover these topics now in class. So we are going to do this collectively, and none of it is that complicated that we can't do it with the background we have. I want to spend the time on superconductivity, which is totally non-trivial. So then the next thing I was thinking is what will be, this is a topic which is not just of interest, this spin polarized tunneling, magnetoresistance, magnetic tunnel junctions, spin filters, spin valves. It's of huge interest to many other people in our department. So we shouldn't keep them out of it. They should get to hear it too. So I'm notching up now the level of these presentations. You don't just get to prepare and just come and give a talk. We have to bring it up to a certain level. If it does not cross that level, you don't get to present. Because now I'm actually thinking of a conference in which we will have this huge pedagogy section where each of you will have reviewed a paper and you get to give a talk in that conference. And some other people from our Center of Emerging Materials who have key results just on these topics, they also can present. So you get a mix of pedagogy and research. And so I called up Nitin Patture, who's the director of CEM, and I said, what do you think of this idea? And he says, oh, that's really excellent, that's great. And he says, if you can get one person from outside, I can provide food. I was like, what? What is this? That's the part I was hoping you don't record. But anyway, I said, what is this about one person from outside? And he said, oh, there are some rules which basically say that if it's just internal meetings, we can't provide food. So I was like, oh, I hadn't even thought about food. You know, I was just still struggling with topics. But when he said that, I said, oh, okay. So I said, well, you know, Ohio University, right next door, has an excellent nanoscience program. They just posted, just this morning I got a paper from them, you know, nanotechnology or nano letters, they had posted something. So that was on my mind, and I said, hey, we can include Ohio University. And he said, oh yeah, that's great. And then I call up Nancy Sandler, who's a faculty at Ohio University, and she's like, oh yeah, we can, all these students of mine, and now it's like, I was thinking of one day, it's become 2 days, and etc. And so it's grown. We'll try to keep it contained. The problem is the timing, because you guys have exams. We can't just have so much fun, you know, having a conference and all of that. But so I need to get some feedback on, you know, like June 4th is the last day of classes. How busy does it get? Like, could we have it Thursday, Friday, Saturday, Sunday? You know, you guys are probably studying for your exams.
Sounds like a big deal. You could probably get us out of our exams.
I'm happy to do that. But then they'll catch you and they'll make you take it some other time.
So E&M final is
Yes.
early.
It's May 26th.
Yeah, so
Oh.
this is great, but I can't speak for the others.
Yeah.
Well, the StatMech final is on Thursday, and Quantum's scheduled.
You mean Thursday of the last classes week or the
No.
final week?
The final week.
Oh.
And Quantum is Wednesday if he has a final at the final time. He's been kind of ambiguous about it.
We can
He said
even do
that
it the end of your exam week. So 4th is a Friday, 11th is a Friday. We can do it the Saturday. Sunday I'm leaving town. But we can do a Friday and a Saturday. Okay, so let's have some discussion. I'll make a blogger and then you guys can respond to that. But let's find a date, and we may need 2 days. And then it's starting to sound like a real conference, and you know, everybody else is going to come to that. So now our reputation is on the line. You know, we can't give a sloppy talk. And that's why I said not everybody gets to give a talk. If the talk doesn't reach us, and you guys will decide, you know, if the talk doesn't measure up after several, that's why I want to start using my Wednesdays for discussing with you a little bit, rather than just keep lecturing and so on. Just discuss in small groups and try to work through different papers. You know, if you have questions, bring it on every Wednesday, rather than trying to make appointments, because we know that Wednesday 1.5 hours is available. So we try to do that.
So what sort of timing are you thinking for these presentations? Like how long?
How long? I am thinking of lots of discussion, not just the talk. And also, you know, not all these IRG students can just get to come. They have to read before, you know, because now we can, you know, we have to have meaningful discussions, not like, why do you get a charging energy? They have to be at our level. Because, you know, we don't want to be teaching them. We've gone through a class, we know so much. Our chemical potential is here. So they need to be at that chemical potential so as not to bring us down. We are hoping to go up from here through these discussions. So we absolutely want them to go through all the material we have covered. We are not going to cover nano dots again. So if they don't know that, they should read up. So that will be a requirement. And so I'm thinking, I don't know, you should tell me, but what do you think? What would be a short talk and then maybe discussion after every so many talks, or we can have a program committee among all of you. You know, we can, and then you guys can put together the format.
March meeting talks are 10 plus 2 or 8 plus 2?
They are, you just went.
So they're
Or
like
blurry boundaries.
Yeah, it's sort of blurry, but it's like 10 plus 2, I think.
I don't know, is that?
That sounds good, yeah.
I think it depends on how much time, total time we have divided by the number of
Yeah, that too.
We can also control it by just 10 plus 2 and then however many we can fit. So anyway, here it is, and what I'll do is, you guys should, among yourselves, form a program committee. You know, find a chair of the program committee, find the group, because you know, it'll be a good learning experience how these things are done. And then you know, you get to decide, and the program committee gets to decide which talks will be given, which fit in with the theme, you know, because I can imagine Ohio University, I told Nancy, send me a list. And she said, oh yeah, we have a lot of people who are very excited. So there will be a list with 15 possible people who want to speak.
So is there a theme, or is it third quarter condensed math?
No, the theme is, has to be drawn from this article. This is our driving article. Some kind of spin, it doesn't have to be spin polarized tunneling, some aspect of spin transport, or spin tunneling, or spin tunneling and transport. That probably covers all of GMR and everything. Any other questions? Does this sound exciting? You know, at least it forces us to, you know, we can get away with anything among each other, right? But now we can't. So at least it forces us to raise the level. And my reputation is on the line. You can't, you know. So, okay. So we'll have some more discussions on this. Okay. What I want to do is try to finish the condo effect today and discuss that experiment. So let me just recap a few things. Basically, the condo effect is, when they say condo effect, so the effect is usually referred to as the resistance minimum. So this effect is usually the minimum, resistance minimum as a function of T. Okay, that's the effect. And this minimum happens at a temperature of order Tk. It's always in a system in which you have a magnetic moment in an otherwise free electron metal. There's also, so this is the condo effect. And the condo problem, you'll see this word also, condo problem, suggests there's a problem. And what does that refer to?
The log divergence at low temperatures. So if it were just like log T contribution to the resistivity, then it would average.
Yes. So the problem refers to the fact that rho goes like rho of T, or R of T, doesn't matter, goes like some R0 minus some R1 log EF over T, or plus. So there's a log divergence. At low T. That's the condo problem. And then finally, the fix. The fix is the scaling theory. Which tells us this. This is the ultimate result of the scaling theory, that you have a crossover. Okay, so this dotted line here signals a crossover. And the reason I'm stressing this is when I come to superconductivity, I will talk about a phase transition. Okay, that's a whole different ballgame. A crossover is where you see a change of character. So on the high temperature side, the system behaves like it has a local moment. And what does that mean? It basically means if I measure the spin susceptibility, chi, it will do what? Ishi? If I have a local moment, what does the spin susceptibility do? This is from, I don't know, somewhere.
C over T?
Yeah, it'll do C over T. Okay, there's a temperature. So when you have a single moment, which is flipping, a non-interacting moment, right? You might have done a stat mech class on something like this. Just a spin-half system which can be in two states. And you do the thermodynamics of that. You will get some constant which depends on the size of the spin, S times S plus 1, etc. But then the important thing is the temperature dependence has a 1 over T. Okay? So that's the behavior on this side. And then when you go below Tk, which is some characteristic scale, and this scale is not easy to calculate. It is obtained by the scaling theory. You cannot get it by Kondo's perturbative technique. The perturbative technique goes this far, but cannot calculate this temperature scale. Because it's more or less a high temperature expansion. I mean, it's a weak, they have not been able to, in this perturbation, you're only able to look at a few terms. You're sort of describing this region. So this characteristic scale comes from the scaling theory, and it has a form which is of this kind. I will draw it there, and I will give you the expression. But then the point is the system changes character, and below Tk, what's happened is you've formed a singlet, the local moment here. There was a nice big local moment. Let me use my chalk colors. So here was this local moment, and here it's formed a Fermi liquid because the local moment has formed a singlet with the electrons. So that's a singlet. And once it's formed a singlet, we have recovered the original kind of non-interacting metal, almost, a Fermi liquid, except for certain resonance features in the density of states, which I'll come to. But in terms of the system, it has become a Fermi liquid, and so its chi now looks like what? Anybody remembers? What is the susceptibility of a Fermi liquid as a function of temperature?
Constant.
Constant. So this is a constant.
So isn't that like that plateau that we saw yesterday? That's like another temperature scale even lower than Tk, right? Or
Well, it starts to happen, so nobody defines another scale, but basically around here it's some fraction of Tk, but in terms of something setting the scale, it is this quantity, Tk.
I see.
So it's also called a coherent scale, meaning the singlet is starting to form, and then at some point it takes over. Okay, now the calculation of Tk is a bit complicated, but as we talked yesterday, from some kind of a Hamiltonian, SD Hamiltonian, which basically looked like J S dot S, this is the conduction electron spin. And this is the local moment. Through a detailed scaling theory, which I cannot go into, the Tk can be found to be of this form. KBTk is basically some set of constants, let me just write here D, and take a good look at this, because in the superconducting case, I will derive a temperature, the transition temperature, which will have a very similar form. So D is some kind of a cutoff to G, G0, EF, to the 1 half, e to the minus 1 over 2G. So even if if we can't derive it, we can still understand its importance, and I want to dwell on that. Okay, so D is a bandwidth. Bandwidth meaning when we had a tight binding problem, there was a cutoff in our bandwidth. It was 2 times the hopping or something. Right? So bandwidth is when you look at the dispersion of the bands, it goes from 0 at the gamma point to some value at the edge of the Brillouin zone. That width in energy is the bandwidth. So this is the bandwidth. J is that antiferromagnetic coupling between the spins. G0 is the density of states of the copper metal before you put the local moment in it. So G0 is basically the density of states at EF for the metal. For metal before local moment is put. Okay. And then there's an exponential, e to the minus 1 over something. Okay, so this is a very interesting result, because usually, if you think about most situations, let's say Ising model, where you have a Hamiltonian which is Js dot s, right? In that case, it is a coupling of the of those spins. So it's Si dot Sj, not dot. It's just a scalar. It's just a classical model. So for example, in the Ising model, a Hamiltonian. So here's like an aside. And this is a model I think most of you have seen somewhere in the StatMech class. It would be J, Si, Sj. These are classical spins, so each Si is plus minus 1. Okay, summed over Ij, nearest neighbors. Okay, for this model, the temperature, this model has a phase transition. At some temperature, above some temperature, these are just local moments. They are random up and down. The net magnetization is 0, right? There are equal numbers of up and down. You hit a temperature Tc, and the system gets ordered. And the temperature Tc is basically a number times G. Nobody even cares about that number. It's of order 1. Okay, so when you say what sets the scale for Tc, it's just J. Now here is a different situation. There's J in the Hamiltonian, but Tk is not of order J. Okay, you know, all these things are some numbers, bandwidth, 2, etc. It's exponentially suppressed from the bare scale. That's why this is a very hard calculation. If it was just of order J, you know, you could have just estimated it. But this exponential decrease, suppression, is what requires the scaling theory. Okay, but this is interesting to note. There are very few examples. Superconductivity is another one, where you will see superconductivity happens because of attraction between electrons. And that attraction you can call some scale. Let's say some bare scale. You can give it a name like U. Some attraction scale. Tc is not going to be of order U. It's going to be exponentially suppressed in U. And you'll get a term exactly like this, e to the minus 1 over U times density of states. Because this has to be a number. So this is number of states per unit energy times energy. And volume is after this.
So I have a question about this equation. On the left is in the unit of energy, right? And the J times G is unitless, right?
This is unitless. This is energy.
Oh, D is also
Bandwidth. So it's you know, bandwidth is this. When you look at epsilon versus k, you have something going like this.
Okay.
This distance here in energy space from 0 to the Brillouin zone, right? I'm just doing it in 1D. This is the bandwidth. So it's an energy.
Okay.
So this looks a lot like the quantum dot equation that we had yesterday.
Yeah, okay. So that, yeah, it looks like a lot like that. So the quantum dot equation is a further, I'm coming to that.
Okay.
But this is what was derived in the scaling theory, Anderson, etc. And the quantum dot thing is a further, just a generalization of this to that geometry, the quantum dot geometry.
Yeah, that's what I'm.
But it will have the same exponential form.
So you said the bandwidth is the system before we put ferromagnetic impurities or after?
Bandwidth doesn't change very much. The density of states, this one is before.
Okay.
This one is before, after, whatever. Okay, but take it as before.
Okay.
Okay, because you want all the before stuff. None of the, what is coming in because of the coupling is J, and then the exponential decrease.
Okay. But if we put more and more impurities, magnetic impurities, TC will change and go up, right?
Okay, that becomes a different problem. Okay, so this condo, yes, that's a very good question. So the condo problem originally came up when you had a people were looking at people were not even looking for impurities. They were looking at, as far as they thought, clean systems. So when they saw this minimum, it basically came about from a small concentration of impurities. That itself led to this huge flurry of activity, which we discussed yesterday in some degree, and that was the condo problem. Now, of course, you don't need to accept that. You can start adding more impurities and ask what happens. And what do you think will happen? Do you have any idea? What might start happening? Let's say I take this system and I put in more and more impurities.
TK will go up?
TK may go up, yes, but even before that, let's just think, you're putting in impurities, and the impurity is trying to form a singlet, right, with the electron gas. But if there's another impurity nearby, it might also start interacting with the impurity. So you need other terms here, because you can generate interactions between these big spins, which don't exist in the Hamiltonian right now. So things now become, you start competing between big spin interactions of the local moments, as well as, which is trying to defy singlet behavior, because they will interact only if they are not singlets. And then, the electrons which are trying to come and, surround them and make a singlet. So it becomes complicated. But that whole thing is actually a very interesting problem. Okay, I'll mention that in a bit. Okay, so this is one result. And the other part is, so this is how we get this scale. And the other thing is a very important feature in the density of states. And that is a condo resonance. And that comes out of some of those more fancy theories, especially the beta-ansatz theories. But what they found was that in the density of states, if you look at G of P, it has some density of states for the bare copper. At EF, there is a resonance. At EF. And the width of this resonance is TK. So you can see that it's a very you wouldn't have, so this part just says that you got a Fermi liquid. It sounds like somehow you made a singlet and you recovered a very boring state, which you have known all along. But it left its imprint in a huge resonance.
Will we talk more about that?
Yeah.
Okay.
Like what?
Well, I mean, so you just add these impurities.
Add a single impurity.
Add a single impurity, and you add states at the Fermi energy of the copper or whatever metal. I guess I'm curious about the mechanism. What's happening?
So that mechanism is a little, I can only describe it in words, but that mechanism is what makes this. So the resonance is what makes this a many-body problem. I mean, this is it's just, I can understand if you had a Hamiltonian in which you had interactions, we write Hamiltonians which are just kinetic energy, and then, we've been looking at a one-body potential from the lattice. We can add a term in which two electrons interact. That's obviously many-body, because you have interactions between every two, each pair. This one did not have any many-body aspect. It was just a single moment interacting with an electron gas that was non-interacting. But because of this successive scattering, you see, this is the process we described yesterday, that you have an electron coming in, going out, K prime, and then there was a spin flip. I don't know how I drew it. Did I draw it with some kind of a line? I don't know. These are not some standard diagrams. So this was, let's say, up, it went down, and the spin correspondingly from down went up. So this is one of these processes. Now, this is what one electron did. Another electron comes by, does the same thing. That puts the different electrons that scatter off that impurity into some kind of a coherent state. And that's this resonance that you're seeing. And that successive scattering is what generates a many-body problem. Okay. So that's all I can really say. So let me write that down. Many-body problem, because successive scattering of electrons from the same impurity leads to a coherent. By coherent, you know what I mean, the phase. When I say two beams of light are coherent, I mean they have the same phase relationship. So that's what I mean. Lead to a coherent, meaning they are in the same phase or something, or they have a well-known phase shift. So I'll just write coherent, because I'm not writing down a wave function. Leads to a coherent state, and that shows up. It's completely non-trivial. Nobody can predict these things. It comes out of a calculation, and then you can use these words, but, or maybe that's just my level of understanding this problem. Because it is true. When they say you have to be able to explain it to your grandmother, the more you understand it, the better you can explain. That is really true. When I tried to explain things to my grandmother, she would never believe that people had landed on moon. How do you convince someone, with all the pictures? So that was where we had to leave off. What? Your grandmother also?
No, it was a moon landing hoax.
Coherent state that shows up as a resonance.
So is there some experimental signature on this resonance?
Yeah, that's the discussion today. You should get one of these.
So I actually just came from a student talk where he was
Yeah,
measuring-
David Goike, right?
Yeah, he was doing STM, and so he was
On a
measuring
cobalt atom?
differential conductance, which is a map of the density of states, and he pointed to this peak and said, this is the Kondo resonance.
And did you ask him what's the proof?
So no, I was confused at the time because I didn't remember that this peak in the density of states shows up, so.
Okay.
So now I'm
Yeah, we didn't
kind
discuss
of up to
it.
speed.
Yeah, we didn't discuss it yesterday. We are not going to do it now. Yeah.
So is this Kondo resonance low temperature effect?
Yeah, only below TK. Only below TK. Because it is a coherent state, right? Above TK, the local moment exists. Below TK, the local moment is quenched. By quenched, I mean it has become a singlet. And it leaves its imprint as a Kondo resonance. So only below TK, but T less than TK. Okay, now, what we can say right away, let's think about what kind of consequences could we have if you have a huge density of states. What does that mean? You now have at EF a huge density of states. What would that imply?
Large conductivity.
A large conductivity is complicated because you have density of states multiplying scattering, so both things go up. Density of states goes up, but since density of states has gone up, scattering rate has also gone up. Right? So when you do any squared tau, so you're, okay, let me erase this because this is a useful discussion. So large density of states at EF. So one, you might think that, okay, conductivity or resistivity, which is proportional to density of states G of EF, times, we write it as any squared tau over m, but you remember we went through this whole discussion. It's not just total number. I'm relying on you guys to remember that. This is ne squared tau over m. N is the total density, but really it came from the fact that transport only looks at electrons at the Fermi energy, and we got a density of states, which we then wrote in terms of n. But the real effect was density of states times tau, but scattering rate is also proportional to G of EF. Right? Because
It's not just impurity density. This is
yes, so there is also there is an impurity density and a density of states, both. Because we went through some of these integrals, w, k, k prime, etc. So it basically is a matter of, you scatter from k to k prime. How many states are available? And that brings in a G of EF. So the density of states kind of cancel in this, roughly at some lowest order. So
I think the system will be very easy in a non-linear regime because when you do a conductivity measurement, you are probing the electrons near the Fermi surface. But by applying different potential difference, you are probing different electrons, different number of electrons.
yeah, but do you really want to go away from the Fermi energy? You want to stick near the Fermi energy.
Yeah.
Yeah, so you don't want to go away. But I agree, you can apply a large bias and go outside the linear regime. But, so we are not really talking about how to measure this density of states. We are going to come to that. In a tunneling experiment, you could get it. But it can have consequences in other things. For example, yes, specific heat. Specific heat is directly proportional to this gamma factor. Specific heat we showed for an electronic system was gamma times T. And gamma involves an effective mass. You remember that from the first class? Gamma was an effective mass over m. It involves another density of states, basically. The specific heat was proportional to a density of states. And G, just simply G is, MKF is m star, for an electron gas over h bar square pi square. So the important thing is this m star. So if you remember, I mentioned these heavy fermion materials at some point. I was talking about Fermi liquids and I said, cerium, aluminum, and uranium, palladium, and there were these strange materials I showed you which had very large effective masses. This is the mechanism by which they acquired that. And at that time I remember some of you asked me, why, I'd never heard of this, why are we bringing in cerium and where are these things coming from? These are all F-shell electrons, which have local moments. And you want a local moment which is sort of deep, right? It is interacting with the electron gas, but it's not tunneling from that localized level so fast as to just melt away into the electron gas. It remains a local moment. And F shell electrons are very deep, so they retain their local moment character and they can form this resonance. So that entire class is basically this heavy fermion comes from a Kondo mechanism underlying that. So we've sort of at least come to some understanding of that. Okay, so now the most fascinating aspect of Kondo effect is, of course, that the singlet is formed, but the most fascinating aspect is that there is that Kondo resonance. And that had never been seen in the bulk. Even in heavy fermion systems, they cannot really see that. Because the tool available is let's say, photoemission spectroscopy. You send in an electron, you send in a photon, and you excite an electron. And then you look at the energies at which you excite the electron. That's G of E. But now to get that resolution of TK is about 10 Kelvin. So TK is about 10 Kelvin, which is about 1 Kelvin is 10 to the minus 4 eV, or it's 0.1 MeV. So 10 Kelvin is 1 millivolt, and that's a very high resolution required in these things where you're exciting things at EV energies. So tunneling is the perfect example where you can hope to see this. So let's now focus on tunneling in dots and see what they are getting at. Okay, I'm going to erase all of this. Can I do that? Okay. And we move to tunneling in dots. Okay. Okay, so we started to discuss that, and let me just quickly set it up now. So this is tunneling in a quantum dot. Okay, so let's say I have a situation like this. I'm going to draw my quantum dot like this. Here is the quantum dot part, and these are my leads. So this is the lead. This you can call a drain and a source. And I'm not going to look at nonlinear transport. I'm going to basically just make a slight difference in chemical potential to pass a little current. So that's that, and here's the dot. And I can have different numbers of electrons on the dot. So I can have something like, okay, and I have a gate. Okay, so I have a gate coupling here. Which basically says I have many levels, and bit by bit different levels are brought into this dot. So V gate controls N. So I can have something like this. As I change V gate, I would get something. Initially there is no electron, then 1, then 2, then 3, like this. There is a little reason why I made one bigger than the other, which I'll come to.
This is current.
This is, I'm just writing number. So I'm plotting the number of electrons in the dot. And I can get this, actually what I will be measuring is a kind of voltage or a current, but actually a current. So there's no current, so you can think about it as current. IDS. Or you can think of it as N. Okay, so there's no current initially. Then there is a possibility of one level coming in resonance. When that happens, there's a current, that's the current, and then it remains constant at that level, and then another one, and then another. No, the current would go to zero. The current would go to
These
zero.
Coulomb blockades, right?
So the current would go to zero, right? Because now there is, because the current I'm defining as just, so let's see, one level comes in conjunction. So I get current at that point.
Right.
But then it goes out, and then I don't have any other level. So I don't want to plot I. Let me just say I'm going to count N.
Yeah.
So that's just the number of electrons.
Yeah.
Yeah.
So this is the number of electrons on dot. So here N is 1, here N is 2, N is 3, and so on. Okay, so let's take a situation where we have, let's say, one electron on the dot, okay, an odd. So basically we're going to see odd and even effects. So let's say we have N is odd and versus N is even. If N is odd, the total spin has to be half integer. If it's even, then S is equal to N integer. So let's focus on just one electron. So S is half. And that's good enough for us. So I'm going to draw 3 pictures which tell us about tunneling from an initial state to a final state, through a virtual state. Okay, so initial, virtual, and final. So in the initial state, I have, these are my leads, I have an electron here. This is my level in the dot. So this is E0. And the situation is the following. I have a single electron, let's say, with spin up. And it's trying to hear these funny blue lines which don't go away. Because now it can really muck up our thing. You know, it's like, is it seeing another electron there or what? And here is a down electron in the dot. I mean, in the lead. And so a virtual state, as you know, when you do quantum mechanics, you go from one state to another. A virtual state is basically all the excited states that you could go through, right? So the point is, this is, let's say, the energy level for one electron. If you just solve the dot eigenvalues. Okay, so the way to understand this virtual state is to say, suppose I have a dot and I want to put in one electron. Where will it go? Well, it goes here. If I want to put in a second electron, we may think it will go into the next non-interacting level, which is somewhere here because of size quantization. No, in fact, we will think the next electron will go in the same level because Pauli is not blocking it. So the next electron will go there, but actually it's the Coulomb, as we have discussed, which pushes it up. So the Coulomb energy tells us that the eigenvalue for a 2-electron problem is going to be here. And this energy is U or E square EC. Okay, is that clear? That we are looking at eigenvalues of many body systems. We are not just now doing our usual 1-electron problem and filling up. We are actually, so when we want to know what is the eigenvalue for the second electron, we have to start with 1 electron there, and the second electron is going to sit on the upper level. Okay, so what happens in the virtual state is this electron tries to tunnel on, and it's going to come to this situation. Now there are going to be 2 electrons in this situation. So here is one of them, and here's the other one. Blue. That's the virtual state. And then the next level, final state, is something like this. The blue is here, and the pink is here. Sorry. So why am I drawing it like this? There's an exchange coupling. Yeah, question?
Should the Coulomb interaction raise the energy of all involved electrons? And I don't see how you can keep one electron at the lower energy level, because that energy level is no longer okay.
Yeah, so this is just a way of drawing something. What you have to do is, it's a bit hard to really depict it, because what you're doing is you can only calculate the energy of a 2-electron problem. That's what you can do, right? If you look at the energy, you have a Hamiltonian and you put 2 electrons and you can say, well, what's the energy of that? And what you will find is, in this case, the energy was E0. In this case, it's not 2E0, but it's of the order of E0 plus EC. But everything has shifted. Yeah, you're right.
So we're saying that the energy of the system as depicted will just be the energy of the highest drawn electron. Is that correct?
No, when I do my perturbation theory, I don't need to know which levels are being filled out. What I'm going to do is I have some initial state A, right? I'm going to go through a virtual state B. So let's just call it I, some virtual state A, and then I'll have a final state F, right? So I just need to know EA minus EI. That's what will go into the perturbation theory. And EA is a well-defined number. I don't need to know what specific levels I've filled up. I just calculate the energy of 2 electrons. You see what I mean? And it will be essentially bigger than the original one by a number of order. It won't exactly be E square over 2c either. It will be of order E square over 2c. There could be some size effects and so on. And that's all I really need.
So we did draw this picture yesterday with both electrons up in the higher level.
Both in the higher level. I guess that's the part. It's not very well defined. So I don't know quite how to draw that, this virtual state. Because what it is, so think of it this way. Yeah, question?
That just seems more accurate though, right? You now have an interaction energy which raises the quantum well states. And because they're not polyblocked, they'll both occupy that lowest quantum well state.
Yeah, so let me explain why this doesn't work. I mean, this way of putting them in a state, because you have to ask, what is that state? Okay, so that's why this is a little bit, and all the papers I looked at are very confusing about it. Most of the papers show the virtual state as being things happening in the leads, which is even worse. So let me just say what I want to do. These levels are very easy to draw when they are single particle levels, right? Then I say, okay, here is a box,
Okay.
here is a single particle level, here's another single particle level. I solve this problem without putting any electrons in. Now I start to I put one electron in, and then I can put another one here. Or if you tell me there is a Coulomb repulsion, well, there is another state way up here. Okay, this is how one might argue. This was the first level. Because of Coulomb repulsion, there is another state not quite there, because Coulomb is much bigger than this. So this is, let's say, delta E due to size quantization. And this is, let's say, Coulomb EC. And you say, well, I'm going to put another one here. But that's not correct, because as Rick said, all the levels have shifted. But it's not just that the levels have shifted, the levels don't really make sense to draw them like this. So what you have to do is the following. We can very clearly state the problem we need to solve, because what we want to do is, we have a Hamiltonian, which is a very simple Hamiltonian, which is just E squared over Rij. That's all it is. That's the Hamiltonian. Now, we need to, so what happens is when there's one electron, this doesn't play a role. So, it's some zero.
So you think the gate voltage is zero because there's a gate voltage potential?
I'm sorry?
There's a gate voltage. That's zero.
Don't bring in any gate. Right
No,
now,
no gate. Okay.
I'm just talking about a pure Coulomb Hamiltonian. The
Okay.
gate just allows you to put more and more electrons on the dot. So what I'm saying is now we have to get the energy as a function of n. So we have to get a spectrum for each value of n. Okay, so let's at least go through this exercise in our mind. Here's the Hamiltonian. I want to get the ground state and excited states for one electron. Well, it's just zero. There's no other, there's no interaction. So let's say for 2, right? So now that's what we are trying to do here. And for 2 electrons, it's going to be basically E squared over sort of R, because they will try to be as far away in the dot as possible to minimize the Coulomb energy. So it's going to be E squared over R. So let me write that down. So we want E of n. Okay, so now for 2 particles, so n equal to 2, we have a ground state, E0. We have to get a spectrum for every n. Okay, so for 2, E0 is just E squared over R. What is the excited state? E1. They can move around. If the 2 dots are slightly closer, and it's a continuous situation. So any R is a continuous variable. But each of those is some kind of a excited state. So we can get, by varying R, we can get a whole slew of them. But now think of 3. Suppose n became 3.
Is n
The number of electrons.
these electrons on a single dot? Okay,
Yeah,
all right.
right. So previously you could just take the levels and you didn't have to recalculate the levels. That's what I'm trying to bring up. The levels were, predefined, and then you just fill them up. Now for each n, you have to recalculate the eigenvalue spectrum. And clearly for 3, now, say you had a dot, if it was a line, let's say, the dot is actually, a 3-dimensional blob. But let's say if it was just to illustrate, we said in this case, this is the dot. This is my dot depicted as a line. They are sitting here and here. Now when it's 3 of them, they will sit here, here, and here. That's the most optimized form. And this will now give you another E0. For n equal to 3, I will get an E0. So I will get some E squared. E0 will be E squared over, this is R, so I get R over 2 squared. R over 2. and then plus another one. And then I have various excited states. So obviously when I went to 3, all the levels are shifted, exactly as you were saying. You can't just go back to that. Question?
I was gonna say that's the third term in that one, right? E squared over R.
Between this and this? Yes, you're right. You're right. And then an E squared over R. Very true. And then, so on. So basically, if somebody could actually measure the reorganization, that would be a great experiment. So you have, for example, 2 electrons on the dot, and they are sitting a certain distance apart, physically on the dot. And then another electron starts to tunnel. Of course, you don't know that electron. So because there's communication, there's a little bit of tunneling. At some point, all the 3 electrons, all the electrons will shift to accommodate that new electron coming in. So there's actual physical reorganization of electrons to minimize Coulomb energy at every point. So that's kind of what is involved. But people are very lax about these levels and what they mean by that. But this is really what we mean by the levels. But yeah.
I think it's a good idea to think the quantum dot as a capacitor. You have, say the charge is Q, so the total energy is Q squared over 2C.
Yeah.
Q is just
that gives us the order. That gives us the order of magnitude. I agree. Yeah. But what I'm trying to discuss is, what we mean by these dotted levels.
Okay.
Yeah.
Yeah, I have no problem with that.
Yeah. So actually, so now let's think of it this way. If we had to draw a diagram with this, we would find the ground state. So I'm going to modify that picture in a bit. What I should do is for 2 electrons, I should find some eigenvalue, which is the ground state, and put both of them in that ground state. Yeah, so I agree, I should do that. And so yesterday what I drew was correct. So let's just draw it like this. I'm sorry, now again this won't let me, it makes me pay for my sins. Anyway, so I want to be sure everyone understood this, because this is a level of discussion which doesn't exist anywhere, but now that we have figured it out, we might as well make a point of it. This was the single particle level. 1 electron went in. We do this Coulomb calculation with 2 electrons. We get the ground state of 2 electrons, which is necessarily higher over and above the 0 by this much. So that's where it is. So here was our E0, which is the dotted one. Here is now this is the n equal to 2 ground state. Okay? And in this ground state, we have solved, when we solve this, we have solved for 2 electrons in this ground state, so that's where they are. I should change the color. We cannot do that. Even though they are distinguishable, we will exchange them in a bit. That and this. Okay, therefore there. So that's the n equal to 2 ground state. And then one of them tunnels. And now, of course, you can have many processes, some without exchange, some with exchange. The one that interests us is the one with exchange. So the up one hopped out. Why did this hop down? Just because that is the ground state of 1 electron problem. And so now we know how to do 3 and so on. Yeah, Megan?
So the difference between like E0 and that value n equals 2 for that's the ground state for 2, you said is E squared over R, but it's also, is that also the same as the charging energy?
Yeah, because
Okay.
C is R.
Oh, okay.
Again, not so worried about 2s and so on.
Okay, so that is
is
that
also
is the
R.
same thing. Okay, just because we were like
Yeah, yeah.
messed up.
Yeah.
Why is the red electron get out, not the blue one?
They are both indistinguishable, right? So both processes are happening.
Okay.
Yeah, you have to remember that. This is a tunneling process. You have both processes. You have processes, so this is all described by a Hamiltonian of this kind. What you are seeing is a tunneling event from here to here. This has an amplitude t. Here's an intermediate state. So in this intermediate state, has an energy E which goes like EC, which is E square over R, and then a final state. So a final tunneling event, which takes you out of this. So what you end up getting in second order perturbation theory, I'm not deriving this, this itself is a very important calculation for many things, is that you get a term which looks like this. So this is, in second order, as you know, you go from one state to an intermediate back to another state with an energy denominator. And so this is EC, sorry. I keep using U because of high DC where we have U, but it's this. So you go, there are two tunneling events which take you from I to A, and then A to F. So those are the two T's. Those are the T's here. And then in between there's an intermediate state which has an energy difference, relative difference between the initial and the virtual state, which is EC. So you get an exchange coupling which is of this order, T square over EC. And this exchange coupling then comes in as a J little s dot big S. Okay, this is the net Hamiltonian. So this term, as you know, these are operators, right? So there is a term which is SZ, there is a term, and that would be something where you don't flip the spin. But then there is a term which is of this kind, right? You have all those three terms, G, little sz, big SZ, plus, let me write it out. So this Hamiltonian, HSD, which we have essentially derived here from these microscopic processes, is J little s dot big S, and that is J, it has three kinds of terms, SZ, big SZ, plus half, S plus, S minus, plus, S minus, S plus. Okay, so this basically says there is no reason why I have to consider a blue down. Blue can be up as well. So, the Hamiltonian encapsulates everything. You can flip this, flip that, just have Z terms and so on.
So the little s is the spin of a blue electron?
Yeah, little s is the blue one. This is the blue.
Red is big.
Yeah. Conduction and the local moment. So the dot is defining a local moment. Previously what happened was you put in ion, and ion has a net local moment. Now it's the dot, which is very nice because it can define this local moment. Okay, now today is my last day to say. Let's look at that data. Okay, so you look at this data and tell me what you see. Let me sketch it, because then we can. So I've sort of defined this in all the terms on this sheet. And basically what is being done is this axis is still Vg. Okay? Now what you're going to do is you want to look at the current through this. The one we were trying to draw earlier. And to get a current, I have to imbalance the two leads. right? So I imbalance them just a little bit. That's why the vertical axis is di dv source drain. So the two chemical potentials slightly imbalanced, and I'm going to the limit where the voltage goes to 0, that's the conductance. So that's what I measure. And let's try to draw it at 0 temperature. So this is G here, and this is Vg, and let's try to draw it. So here, okay, and what we expect is basically it will be 0, then we will get a current, 0, current, that's what we would expect. Okay, let's see what they actually get. Okay, what they actually get is the following. So this is what we might have expected. This is expectation, right? You all agree with me, right? I'm not, yeah. Okay. Now what they actually see is this. Let me just sketch it at 0 temperature. So at 0 temperature, what they see is this. When it is odd, it is this. I think I get this right. This is n equal to 1. This value is 2e squared over h. When it is even, it is indeed 0. That's what they get. So this is odd.
Is it strange?
As in strange. As in strange. And it's happening on the odd electron places. So when n is 1 or n is 3, at 0 temperature, they get perfect transmission. The most transmission you can have from one channel, from one mode, as we discussed, is 2e squared over h. And that's what they get. Then when they are even, if it's even, they get 0, and then again this. So now let's see how does that gel. Once you have this picture, let's look at the actual data. So the actual data, okay, look at one of these plateaus, one of these dips here which says n even. Okay? Basically what you're going to see is two very different temperature dependencies for the conductance, which I have spelled out on the left hand side. And I want you to correlate that behavior in the data. So what you're seeing is whenever n is even, the conductance is going to go down as the temperature goes down.
Yes.
So you have to check that.
What are the colors?
The colors are very nicely chosen. I wish my students would do that. Blue is cold, red is hot. And sometimes I get a whole splash of things, magenta, I can't make sense, but this is nicely chosen. So look at it. In the even regions, as you make it colder, the conductance is dropping. So it's looking more like this. It's going towards 0. Okay? In the odd places, as you make it colder, the conductance is rising and going toward this limit.
Why?
Unitary limit. That's the resonance. That's the Kondo effect. Okay, so you're seeing very different behavior for the two. One of them, so this one, so the way to at least give some words to it, this is now the Kondo resonance effect, Kondo effect. And this is the Coulomb blockade effect. So in one case, Coulomb blockade is preventing current from going in. In another case, because of this Kondo effect, the conductance goes in a different direction. the conductance rises logarithmically. Okay, how do we know that? Well, look at page 2. Page 2 is nice. It shows 3 sets of data at 3 values of Vg. So you pick one of these odd, on this plot, the first one where you have n plus 1 odd, they have taken 3 values of Vg around there. Okay, and they have plotted in more detail the conductance as a function of temperature for those 3 values. And you see the top 3 red lines, they are kind of scattered. But then they basically use Tk as a fit parameter. They don't know what it is for each of those 3 values, but they use it as a fit parameter, move things around and plot that inset, the blue inset. And the blue inset is not as a function of temperature, but it is as a function of that scaled variable Tk. And lo and behold, everything falls on one curve, at least below Tk. So the data is what you would call scaled by one parameter.
This data is on a single quantum dot?
Single quantum dot. Yeah.
So in the bulk, at least, we said that the Kondo effect is a resistance minimum.
Yeah.
But in this, it's showing that when T is Tk, the conductance is the minimum. So
Right.
Doesn't that mean that resistance is?
Yeah, so it goes the opposite way in dots because of the way, when in the bulk, essentially you're looking at scattering. Okay, so you get enhanced scattering. That's a good point. There is that difference. The temperature dependence is identical in terms of being a logarithmic dependence, but in the bulk, you get enhanced scattering from that impurity, so you get an increase in resistivity. Here, because of the resonance, you get a channel of communication. So what you're seeing is something absolutely amazing. You're seeing a transparent barrier. How on earth did that happen? Because you see, suppose I gave you this situation, okay? Let's just kind of stand back and just try to understand how remarkable it is to get such a perfect transmission, because that's the maximum you could have gotten. You are in a situation where you have this big difference between the Fermi energy and the localized state. If I'd asked you what is the transmission, you'd say, well, there's no state here. There's no question of any transmission because that state is so far away. But it formed a resonance right at the chemical potential. So if I try to plot the density of states on this axis, I have a huge resonance here. It looks like this. Let me try to draw it better. I'm going to stop very soon. So if I try to draw the density of states of this metal lead, it has gotten modified to something like this. And then near this, there is a broad bump. This bump is this gamma. It's just the width of this level because it's anyways allowing some tunneling with the lead. But this I should show even sharper. So this is that resonance. And because of this resonance, the electron is able to somehow tunnel with perfect transmittivity across the whole junction. So it's pretty remarkable. And you see this temperature dependence, which is completely opposite in the odd dot and the even dot.
But this only happens when the electrons, the number of electrons are odd.
And the number of electrons is odd. When it's even, you get the expected exponential dependence.
Yeah, I mean, why we can only see this when the number of electrons are odd?
Because you can only form that Kondo resonance when it's, when it's even. There is a little bit of a wrinkle here, but we have to stop.
Okay.
So the point is, okay, let me say, when n is odd, right, you are guaranteed a half integer spin. Okay? When n is odd, you have a half integer spin. I think I have it here. Half integer spin. So this very quickly leads to the usual Kondo effect. of a spin half. This is like a spin half Kondo effect. You know, condensed matter, it's like never a dull moment. This is one of those. You know, you think, okay, now we understood it, even, odd, we have it all under control. Well, you know, the story doesn't end there. When n is even though our class has to end, it becomes an integer, but nobody said integer means 0, right? Integer can also mean 1. So, integer spin. Now, what I have described to you is when s is 0, you get this effect that they have seen in the even ones, that it basically acts exponentially in temperature, and it goes toward this Coulomb blockade. If S is 1, you can have something more, another kind of Kondo. It's like a 2-channel Kondo, okay, which we don't need to go into. But basically you can have Kondo, it's like more channels trying to form singlets with the electronic cloud. You know, it's a bit like that. So, but at least for now, we will keep this discussion simple and just say that even ones are S equal to total. This is not the singlet between the impurity and the conduction electron. This is the singlet of the 2 big spins on the dot itself. Okay, so when I have put this up and down, this is a big singlet formed by the up and down spins. Okay, that's what I'm talking about. So when it is capital S equal to 0, it does not it just interacts coulombically. There's no spin interaction. And when big S is half, then you get the Kondo effect with the conduction electrons in the lead. Good?
So you kind of spin blockade effect.
Spin block? Yeah,
Okay.
the big S,
Yeah. It's
Yeah.
kind of.
it is like that. It is like that. So in a way, this is like acting as a filter of different kinds of spin states. So you can make, yeah. So this is a very beautiful paper because I looked high and low for one paper that had everything. These little blips here, you know, it doesn't go quite to 1 is because there's a little magnetic field. So we are not going to discuss that. But it was the one paper where I could clearly, I found interestingly, many authors could see a lot in their paper. Like they would say, it is clear that even and odd ones show different temperature dependencies, and you're looking at it, and I couldn't see that. And they could see that, and this happened because you can see there's an evolution of data between the first paper, which was by Goldhaber Gordon, beautiful paper, but nothing like this data. And then, you know, you move another 5 years and the data gets better. So this was one of the best data, which shows clearly the temperature dependencies in the 2 dots, even and odd. And what I really liked was they plotted unscaled data, because that makes the point really clear. And it gels with all our discussions. You know, when we looked at Drude conductivity, you clearly found when you plotted sigma versus omega, for different taus, you got different curves. But then if you scaled it with tau, everything fell on the same curve. It's that physics that is happening here. And it's very important because this TK, and I'll stop right after this, TK depends on 3 parameters. It depends on gamma, it depends on E0, and it depends on EC, what I call U in that expression at the bottom. It depends on 3 parameters. But ultimately, it depends only on the combination, because the scaled stuff just scales with 1 temperature. So that's very important, because when you are comparing with theory, these are very important clues when you make a theory, because that's how the 2 come together, through these scaled quantities. Okay, so thank you. And